All right.
So thank you to Dan Casper and Andrew Majewski for setting this up, and for Eric Koepf to talk. Actually, it's Dr. Eric Koepf now. So me and Eric go way back. He just got his doctorate in mechanical engineering department at UD, and he teaches in our department now as an adjunct. He's actually going to Switzerland in like, what, a month and a half? Yeah. So he's taking a job in Switzerland at ETH. It's a big lab over there at ETH there. He's going to be building some of these reactors. This guy's a jack of all trades. I've known him for a long time. He did everything. He did the work of probably 5 or 10 graduate students on this project. Okay, he did the electronics, he did the modeling, he built it, and he's going to share his knowledge with you today. So give a warm welcome to Dr. Eric Koepf.
Thanks, Corey. Best introduction I've ever had. All right. So I'm going to try and cover a lot of different areas that I've contributed to in concentrated solar power and specifically hydrogen technology through 3 different roles that I've held as an engineer, one being a graduate student at the University of Delaware, another being a systems engineer at a company in Los Angeles called Solar, and then finally the position that I currently hold as a postdoctoral fellow at Swiss Federal Institute of Technology in Zurich. So we're going to try and get through a lot of stimulating visual presentation very quickly. So as a quick motivation here, so the deal is we've got a lot of solar energy available on this planet, and the bottom line is we just don't use it. But of course, it's more complicated than that because a lot of times you need to be able to store the energy for use later on. The sun only shines a certain number of hours a day, and of course it's available a lot more plentifully in certain areas of the globe. So when you combine that global solar energy resource with this picture, which shows the consumption of fuels and the production of fuels in addition to imports and exports in the U.S., what you find is that the rate at which we consume fuels is increasing and the rate at which we produce them is decreasing. Even though it shows a slight increase, this is due to the very recent natural gas exploration boom. Now, of course, we can talk all day about how to turn this number around the other way and start decreasing our consumption, but that's a different conversation. Either way, what we're always going to have is a need to store energy. So we might as well combine our solar abundance plus the fuel gap with solar fuels. So what can we do? The first thing I'm going to do in this talk is talk about concentrated solar power, which is what I specialize in. And I'm going to talk specifically about solar hydrogen and how we can use CSP to produce solar hydrogen. Then I'm going to talk specifically about a reactor that I designed at the University of Delaware to produce solar hydrogen. I'm going to talk a little bit about a couple other advanced reactors that have been around for 15 years and are at very advanced generations and even commercial production, and then a quick look into the future. So let's start with concentrated solar power. So there are a few ways to concentrate solar power. Everybody knows that you can stick a solar panel under the sun, a PV photovoltaic panel, and you don't need to concentrate the sunlight. You just put it out there. It takes the electromagnetic radiation and produces electrons. You put those electrons into the grid or you put them into the battery and everything works just fine. But for other applications, you need to concentrate solar energy. For example, if you wanted to create a very high heat environment, one of the most common ways, and even in fossil fuel generation of electricity, what they do is they create a high temperature heat source and they expose water to that heat source. They create steam, and then that steam pressure drives a turbine which creates electricity. So why can't we do that using sunlight? Well, the answer is we can, but we need to concentrate it. So a couple ways to concentrate are parabolic troughs, which are very long. So you have a huge field and you have very long troughs that have parabolic shaped reflectors, and then you have a tube passing in the focal point of that reflector, and then it usually tracks on one axis during the day. Concentrated so the sunlight comes in, parallel rays, hits the reflector, hits the tube, and through the tube is passing, in the simplest case, water. And the water turns into steam, and the steam goes to the generator. You can do a similar thing with dishes. Dishes are just like the old-fashioned satellite antennas for your television, except instead of bouncing off that wavelength, you use mirrors and you bounce off the full spectrum of sunlight and you concentrate it onto this little receiver sitting at the focal point and you create a very hot spot. And then the biggest way you can do this is using power tower systems, where you have a giant tower in the middle of the field and then tons of little mirrors that track on two axes, and they always, throughout the entire day, reflect sunlight under this receiver. So in the simple case, you create steam in that receiver, and then you create your electricity that way. So this is a specific example of the company that I work for in Lancaster, California. They have two different receiver towers. You can see they're both illuminated, and thousands of mirrors. And these mirrors are small, and they track on two axes. And this type of technology has been around for a long time. So where they stand right now is really optimization. I mean, this is a functioning solar thermal electricity power plant, and there's many of them like this. It's a very simple technology. Of course, there's many layers of complications, but at the end of the day, all you're really doing is taking this black surface, which is just a whole bunch of vertical black tubes, and you're pointing all these mirrors at them and illuminating them and making them really, really hot and flashes into steam. And you use thousands and thousands and thousands of mirrors to do it. Now at the stage they're at, because they're trying to optimize performance and become more and more efficient and penetrate the electricity market, one area that they looked at that I contributed to was the efficiency of their power delivery system. So that means you can create really fancy algorithms, and it's really fun, and it's very complicated, and they've got programmers to do it, and they've got thermal analysis all day long that shows exactly where you need to point these mirrors. But how do you actually know how much power is being delivered? What are the errors? What happens when essentially all mirrors aren't created equal? They all have different reflectivities. Maybe one's more dirty than the other. Maybe there's curvature. Maybe it's windy that day and it's bending the mirror. So what we developed was a simple way to photometrically determine the power delivery from a mirror. And it was very simple. It was using a very simple camera that we mounted on a tower. And instead of having the mirror track the sun and point to the tower, we had the mirror track the sun and point it right back at our camera. So we were always looking at an image of the sun. So an image of a sun through a camera looks something like these. You can see here the camera is illuminated by a mirror, and this is what it begins to see. So if you process this image, what you end up getting are pictures of the sun. But you can see there's a big difference between these three pictures. One is very round, so that means the mirror is very flat. Another is kind of round, but it's also, you can see it's got pixelation in it, and it's also a lot dimmer in color, in its shade. So that means that it has a lot of dirt deposited on it. So at the end of the day, you can process these images using the pixelation and the curvature, and you can map the real-time reflectivity of the mirror over the entire surface. And you can do this for every single mirror simultaneously. And when you do that, you know exactly in real time what power is being delivered to your receiver. And this makes a big difference for them, especially when they're trying to account for things like clouds passing over the field and how to keep the boiler at a certain temperature, which is very important. You don't want overpressure, you don't want underpressure. So that optimization question is something that's very important to them. So this is what you end up getting at the end of the day by scanning the image of the sun over the entire mirror. Accumulation of that can give you a contour map of reflectivity. You can see this is a very clean mirror that's very flat. It has some dips, it has some areas that are dirty, but these regions up here, it's close to 94% reflective, whereas this one is very poor quality. The red zones only represent about 84% reflectivity. So, what if we want to create steam? We actually want to create hydrogen. What can we do? We have a few routes. So using concentrated solar power and water, what is commonly seen as the transition to this type of energy economy is to make use of the fossil fuels that we currently have developed. That way we don't just run out of them and all of a sudden decide we need solar fuels or we need hydrogen or whatever we need. We can start reforming natural gas, gasifying coal, and cracking oil right away using sunlight and water to create solar hydrogen. Of course, you'd have to do something with the carbon, but that's a different story. And of course, you might say, well, what if you just took a little cup of water and you expose it to super, super highly concentrated sunlight? Could you just directly split that water into hydrogen and oxygen? And the answer is yes, but that would have to be pretty much close to the surface temperature of the sun. And that's really hot, and there aren't many materials that can handle that. The other thing is that for those of you that are familiar with chemistry, you don't want a mixture of hydrogen and oxygen at high temperature. That's a huge explosion waiting to happen. So, for those two reasons, we can use a thermochemical cycle, which lowers the temperature we need, and it separates the steps of creating the oxygen and the hydrogen. And this is kind of what it looks like. The heat comes in our case it would be sunlight. The thermochemical cycle begins. The first step, which is the high temperature step, your oxygen is released. In the second step, which is the water splitting step, you take the product of the first step, you react it with water, and the hydrogen is released, a little waste heat. And what's great about this cycle is that the products from the second step are then the reactants for the first step. So it's completely closed loop. So a specific example of a thermochemical cycle will look something like this. You can use a metal oxide. So this is a standard metal oxide. Could be zinc, could be manganese, could be iron oxide, whatever it is. And in your solar reactor, you reduce that metal into a reduced state, maybe even a pure metal form. You can store it for later. You can ship it around. You can put it on a just like you ship coal around the U.S., you can put it on a train. And then you put it in your hydrolysis reactor where you put water in, you get hydrogen out, and then the product of that reaction is the original metal oxide that goes right back into the top. And you can see here the oxygen and the hydrogen are released in separate steps. So this is the specific one that I looked at. And we'll just focus on the point that zinc oxide at temperatures at over 2000 K can be readily reduced into a zinc gas. You can also add carbon for a different matter, but then the water splitting happens in the second step where zinc and water produce zinc oxide and hydrogen. So of course you take your zinc oxide and put it back in the front and the cycle is closed. So of course the question now is, how do we get zinc from zinc oxide? This is zinc. This is zinc oxide. Zinc oxide is a very common chemical. It's in all kinds of stuff. I mean, just look at I bet 50% of the food products in your home contain zinc oxide. Just look at the back. It's commonly added to foods to be a source of zinc. It's in sunscreen, etc. So the answer is a solar thermochemical receiver reactor. And let's talk a little bit about what that looks like in the context of the one I designed and developed at the University of Delaware called Gravity-Fed Solar Thermochemical Receiver Reactor, or GRASR. So the most basic concept of a receiver is it just has to be a very well-insulated space that can take highly concentrated sunlight through a very small aperture up here and then create a very high temperature environment without letting too much radiation come back out through that aperture. And if you can get the reactants hot enough, they produce whatever, let's just say vapor state zinc, and then you sweep that out and you collect your zinc and you've created your solar fuel in the form of zinc. But there's many different versions and there's many complications to actually making that happen and making it happen efficiently. So this is the reactor that I developed at the University of Delaware, and some key features are that it's beaten down, meaning that the sunlight enters from the top straight down in a very concentrated fashion. So if you imagine this thing sitting on top of one of those towers, and the sunlight comes down and it hits a flat mirror, and the flat mirror redirects it back up, there's going to be another mirror there that then directs it back down to go inside this reactor. So you need what's called a secondary concentrator. So that would normally look like some sort of parabolic dish that would be sitting above at the top of the tower, or could be hyperbolic, and it takes all that radiation and redirects it down into the top of the reactor. The zinc oxide is fed through this series of hoppers that are controlled by stepper motors and actively cooled. There are gas flows. The solar energy enters through this area here. This is called the aperture. It's the point of maximum concentration of sunlight, after which the sunlight comes into the aperture, converging and then diverges into the reactor. And these copper surfaces have to be water cooled actively to keep the whole thing from melting down. It's supported by a huge amount of high temperature ceramic insulation that maintains the cavity temperature. There's a central outlet here for the products. Here's a little tile section view. You can see what I meant by the concentrated light cone coming down. The focal plane here, it's a focal plane, not a point, because of inaccuracies in the concentration technology. And then because it hits one of these reaction tiles, the sunlight hits only here, what we end up doing is creating 3 distinct temperature zones. So as the zinc oxide is metered down through here, hits the surface and starts sliding down, it sort of has 2 preheat phases before it gets really hot and starts reacting. Then the zinc oxide that didn't react exits annularly through here, and the vapor state zinc is collected through here. And you take that zinc and you rapidly cool it in what's called a quench device, and that condenses out the zinc and brings it into a very stable metallic form that you can just collect by hand and filter with a scraper or whatever you want. So here's a closer look at the hopper feeding system. You can see active water cooling lines. You can see the motors that control each hopper individually. Here's a close-up of the feeding system itself, which was over a year-long project just to develop something that could give you a consistent, uniform, thin layer of reactants falling into the reactor at all times. The entire ring of them operate at a very specific resonance frequency with the reactor, so that when you actually turn on all the stepper motors and these resonance vibrators, the whole thing is sort of humming. And that ensures that you have good packing of your zinc oxide inside this hopper system. And so as it's feeding through, the zinc oxide is continually moving down and providing more reactants to be metered by this line here. And these teeth are what scoop, as it rotates, the zinc oxide out of this hopper. So of course, we didn't just think this whole thing up in the shower one day. This was a long process that involved a lot of modeling. You always have to model extensively. This was a heat transfer model that we developed for the entire reactor. You can see this is a section view, and this is showing us the temperature inside the reactor. So isn't it interesting that we can keep all of our metal surfaces on the outside of the reactor shell down to 600 or 700 K, but the inner surfaces up here are 2300, 2400 K. So that's absolutely necessary in order to, essentially what we're dealing with is we want the reaction to operate as high as possible, but we can't afford to let the entire thing melt down in any sort of worst case scenario. So you have to carefully model how this solar energy is going to penetrate the body of your reactor and which areas you have to actively cool. So you can see up here, as I said before, the window area and the aperture area are copper rings that are actively cooled, and that's why their temperature remains so low during the reaction. You can see here, based on our model, the different temperatures that we'll achieve based on different amounts of solar power input. So at the 3.5 kilowatt level, we only reach temperatures of around 1200 K. But at the 20 kilowatt level, we're over 2600 K. And this is plotted along the reaction surface. As I said before, there's preheat levels in 1, 2, and 3, and temperature increases. Additionally, we measure and model the evolution of zinc inside the reactor. So this is a little tile section view, and what you're looking at is, in red, this is zinc mass fraction. So based on a certain solar power input and temperature that's achieved on the tile, we're evolving zinc into the reaction surface, and then we're wondering, well, where does it go, and how do we get it into the central outlet? So we created a mechanism that actually creates a tornado inside the reactor, much like when you flush a toilet. And that tornado sweeps inside the reactor and brings these products off the surface and into the outlet, because if they just stayed there, they wouldn't be useful to us. And you can see the beginning of this tornado shape, and I'll show some other pictures of this in a second. Other types of modeling. What about these zinc oxide particles? How are they reacting? How big are they? If they're very small, if they're 1 micron in size, how do they interact with each other? Are they actually forming agglomerated particles? Turns out that they are. So each individual particle forms together and sticks together and agglomerates into an effective particle, a bigger particle. And that changes the kinetics and the reaction rate and how long it takes for these particles to decompose. So what we did is we modeled the evolution of a single particle composed of smaller particles reacting, and we found something very interesting. And it's due to the fact that the geometric surface area of a spherical particle, assumed to be a perfect sphere, is actually significantly less than the effective surface area of an agglomerated particle because of all the small curvatures on the surface. So the reactive surface area is increased so much, and that's shown in the red line here. So when you plot the critical time that it takes for a particle to fully decompose based on its initial diameter, which is shown here, what you can see is in the black, this is if you assume it's a perfect sphere, and this is if you assume that the red is if you assume it's an effective surface area. For a 50 micron diameter particle at 2000 K, it could take 40 seconds to decompose. But for an effective particle, it's 10 seconds. And that makes a huge difference on how we design our reactor and feed reactants in. So then, of course, we have to test the thing. We got to build it and we got to test it. So that's what we did. We built it, we took it to a solar simulator, which simulates concentrated sunlight. So we don't actually have to put this thing on a tower yet. They've got a bunch of these really, really high power xenon arc lamps. And we blast them into a flat mirror that then redirects the sunlight, the simulated sunlight, and comes into the top of the reactor. And this is the setup you can see here. The lamps are behind these shutters here. This is our beam down mirrors, it's called. This is the reactor with all its data acquisition, its electronic controls, its fluid flow mechanisms, all of its control systems, return systems, and collection systems. Here's a diagram of the experimental facility. You can see these are the 10 arc lamps, how they hit the mirror, redirect this. The red part is the reactor, of course. Here's another couple shots. Here's the back of the mirrors. Here's the reactor in front of the mirror, in front of the back of the lamps. And when we run an experiment, it looks something like this. You can see those lamps illuminated, hitting the mirror and focusing down. And we produce a lot of zinc. In fact, we produce so much zinc that we clog the outlet in almost all cases. This is solar fuel zinc clogging our outlet because we produce more than we wanted to. Now, in addition to high temperature experiments, there are a lot of low temperature experiments we had to do as well. And I'm just going to talk very briefly about one of them, and that's this tornado vortex flow I talked about. The reason why you need a tornado vortex flow is because two things. One, you need to get that zinc out of your reactor like I talked about before, but the other thing is that if any of that zinc that comes off of this surface of the reactor finds its way back up into the top of the reactor and hits this quartz window where the sunlight's coming through, it deposits on that window and zinc is black. So if you start coating your window with black zinc, the sunlight's not coming in anymore and the entire reaction shuts down. So we needed to keep the zinc out of that area and off the window. And you can see here, this is a window that's had zinc deposited on it. You can see the swirling pattern here of the zinc. So we created a device called a vortex ring or vorticulator that consists of radial and tangential jets. We made a low temperature device, full scale. We injected lasers, we shined lasers through it. We diffused smoke into this lower reaction chamber in order to simulate the zinc. And we looked at, using cameras and image processing, the formation of this tornado and how to optimize it. So here's a picture of the device after we made it, and here's a couple images that you see. This is the fully formed attached tornado that we want. This is the smoke swirling and moving back up towards the window, and that's what we don't want. So it kind of looks like this. The process of formation of this tornado is it starts as a bubble and it moves down, and eventually if we can get this to attach to here, just like a tornado attaches, then it's very stable. But if something bad happens and it actually starts to move the other direction, it can go up here and hit the window, which is what we don't want. So here's a couple of images of the tornado forming in the lower chamber and then attaching. And here's a couple images of it moving into the upper chamber. And at the end of the day, we found an ideal operating range with our tangential and radial flows that allowed us to minimize how far that smoke penetrated into the upper chamber. And that's plotted here. So a contact point would be equal to 1. So if these curves got all the way up to about here to 1, that means they've actually touched the window. But anything above 0 is bad. So you can see here we have a very nice, clean operating range. So we operate the reactor under these conditions, and in most cases, we can feel confident that we're not going to have a problem with damaging our quartz solar window. So the reactor I developed isn't the only one. It's just stage 1 of a novel design, and hopefully it'll have many other stages. But there are advanced reactor concepts that have been worked on for 15, 20 years at this point by hundreds of engineers, solar engineers around the world. The first one is the Cirrus Reactor, and this is the one that I've now been put in charge of at the Swiss Federal Institute of Technology in Zurich. And it's a version 3, and it's almost ready for commercialization. It's horizontal, it's based on rotating the center reaction chamber. It's very complicated, it's very cool, and it's very large. So you can see here, this is the lab that I work at in Switzerland. This is my colleague Mike. This is the reactor. It's huge. You could crawl into it. My reactor, I could barely put my head into it. This thing is gigantic. It's 100 kilowatts. Mine was 10 kilowatts. But same basic concept, metal shell, lots of insulation packed on the inside, ceramic bricks, and then balance of plant, bringing the whole thing into its operating condition with pressure sensors and temperature measurements and orientation to sunlight and product collection, product delivery, and et cetera. But where do we test this? You can't test it in those lamps anymore, as lamps are too small, so we have to take it to a solar furnace. So the biggest solar furnace in the world is in the Pyrenees Mountains. It's a place called Adeo, and it's a 1 megawatt solar furnace. From a distance, it looks something like this. It's planted right in the Alps. It's pretty amazing, actually. But what it looks like is this hillside with all these giant mirrors that are flat, and then this huge parabolic mirror, and it's like 10 stories tall. And then sitting in front of that parabolic mirror is the experimental chamber where you put the reactor. So here's a close-up of it. It's absolutely gigantic. So we get the reactor in this elevator, we bring it up into here, and this is of course sitting at the focal point of all this solar concentration. And when you operate it, you can see all these mirrors are shining onto here, reflecting back down into here. It gets really hot up there. This is typically what you see when you're running an experiment, because there's a certain amount of dust, particulate matter in the air that just burns immediately when it gets close to that focal point. So that's the Cirrus Reactor. That's ready for commercialization. So if our tests prove to be, if we are able to hit the targets we're looking for, then the next stage would be to find commercial partners and actually make this a reality. But there are other reactors in addition to the ones that they work on in Switzerland. One is called the CR5, which comes from Sandia National Labs. It takes a different approach. It uses pellets that are coated in reactants and that get burnt one at a time as they pass through, and then the hydrogen generation happens in a second step. But the whole thing's integrated, so it's kind of nice in that respect. Another one is a cerium reactor, which is also very popular now. Cerium has a very high reactive rate, and it uses a porous ceramic structure coated with cerium. You can see this kind of porous structure here, and this tube is inserted. But again, you can see a lot of common features. Concentrated solar energy coming in through a very narrow aperture in order to create an extremely high temperature environment. So, what's the near-term future for this type of stuff? Well, for one thing, concentrated solar power, CSP, in its electricity form is, as I said, a very mature technology, but it's also gaining momentum. And it's just great because the technology of mirrors and towers is applicable to the solar hydrogen side. And so as they develop it and optimize it for creating steam, one day we'll be able to take our reactors and just put them on top of these steam towers and create hydrogen instead of the steam. So this is a company called Bright Source, and they're by far the biggest commercial developer of CSP technology, tower CSP technology in the world. And this is in Ivanpah, California, close to Las Vegas. And they're already building this. This is an artist's rendition, but I mean, it really, if you flew over, in fact, you could Google satellite right now, and you can see they've got 3 of the fields almost completely done. And they're absolutely gigantic. So it's really exciting to see this kind of stuff starting to take off. But even on the hydrogen side, there's a company called, well, it's not a company, it was a project called Hydrosol, and now it's 3D because it's the 3rd generation. They have already developed and are looking for partners to build the first commercial round-the-clock production of solar hydrogen. Same concept as before, and all their reactors are up here. They use a honeycomb structure. It actually operates much like a catalytic converter. So, you know, this has been around for 15 years now, so they're at that stage where they're going to try and sell it. And then combine those two things, CSP and solar hydrogen, and put it in the context of general renewable energy. Remember, we were looking at those maps of distribution of sunlight. There are certain areas that just have so much. And so people are actively looking into ways to get where all the solar energy is concentrated and move it into areas that maybe are more populated and don't have as good of a solar resource. So this project, Desertec, is planning, you can see the orange blocks are concentrated solar power, and they've got this grand plan to just plot them all around anywhere that is a candidate from an energy perspective, and then wind along the coastline, and then use a giant renewable energy grid to bring everything around. Now, of course, there's a lot of other questions that we'd have to ask regarding this picture. You know, basically what we're saying is, let's take the solar resource from Northern Africa and bring it and use it in Europe. So there's a lot of political, economic, social questions to be answered there, and of course this region is very unstable at this point in time anyways, but people really have these plans and are starting to break ground on these renewable energy grid networks. So in conclusion, solar fuels and solar hydrogen are probably a lot closer than most people think, and it has a lot more to do with the current availability of natural gas and its price, more so than the status of the technology. This was an article about the Cirrus Reactor that was recently published in Popular Science. There was another article in Scientific American. There's been articles published in Nature, in Science. I mean, there's a consensus that this stuff is ready to go. We're just looking for the right funding, and we're looking for the right price point of our competitor, which is natural gas. So hopefully one day in the near future you may be able to see solar gasoline, pure. And hopefully that day will come sooner rather than later. This is one of my favorite comments. The dinosaurs are sitting there saying, all I'm saying is now is the time to develop the technology to deflect an asteroid. So thank you, and I'll take any questions. Matt.
So you saying with these solar nuclear power plants, will they soon be possibly replacing all of our nuclear power plants that we're starting to have problems with in the near future?
So if your question is there enough solar energy to replace all nuclear energy, and the answer is absolutely yes. I mean, there's enough solar energy to produce, to meet all of our demands in a single day, in a year, in like 1 second or something like that. I can't remember what the stat is, but yes, it's definitely possible to have a completely solar energy economy. More questions? Yeah.
So, what's your goal in Switzerland? Like, why Switzerland? Is it because technology is there? Is it just a job?
Yeah, it's a good question. So, when it just normally happens in any research field that certain, universities or certain regions end up being experts in technology. It just happens to be that this group in Switzerland is one of the experts for this type of technology. The connection is Switzerland pioneered nuclear power research way back when. So you guys are probably familiar with CERN. and all their particle reaction technology. And so this is sort of like CERN spun off into a nuclear power, basically an applied version of CERN. They were developing nuclear reactors for electricity, and then they expanded that scope to include renewable energy forms, non-nuclear. So they had a lab that worked with concentrated solar power that started in the early 70s, and they've been doing it ever since. So they're just really good at it. And there are other groups around the U.S., national labs, University of Colorado, University of Minnesota, Florida State, Sandia National Lab, NREL, of course. So there's a few around there as well. This is a group that I had already worked with previously, and in my opinion, they're the strongest group in the world. Matt?
According to what you were just mentioning about the different companies, what about the areas that don't reflect as much sunlight? Is there a processing plan, plan and process to the less dense sunlight areas? Like up in Alaska, you know that they only receive, basically they lose half a year's sunlight.
Right. So you have to think of it in terms of the less sunlight that's available, the more mirrors you need to create the same high temperature environment. And those mirrors and that tracking system is the most expensive component of the entire system. So that's why, from a price perspective, you want to talk about dollars per kilogram of hydrogen that you produce. You want to put these things in the desert. You could make them work in Alaska, but it would cost 100 times more, and you wouldn't want to do that.
Are they gonna make some type of a channel, like like we have, like right now with electricity? Outside of the technology we use through just waves, electrical waves and stuff. But you know how across the ocean already they have cables under the water that for short distances right now, that they take electricity from one place to another place that doesn't have electricity through power lines, communication lines and things of that nature. Well, along with the...
Yeah, there's going to be, if you're going to have a total picture solar energy economy, the key feature there is to have all the grids linked together.
Okay.
We need to be able to give energy produced in Arizona at noon to energy, transfer it over to energy that can be used in New York at 6 p.m.
Okay.
And to do that, you need to upgrade the grid and connect it all. Yeah?
Can you clarify the final applications of using this hydrogen?
Well, hydrogen or zinc or reduced metal, whatever, it's just a form of a solar fuel. So it depends on what you want to do with it in the end. If you want to use hydrogen in a fuel cell, then you'd want it in some sort of compressed form, maybe highly compressed. If you wanted to use it in an internal combustion engine, which you completely could, there's no reason you wouldn't be able to do that, then maybe it would be a little bit less compression. If you wanted to use the solar fuel in the form of zinc in a battery, well then you wouldn't even create hydrogen in the first place. You would just use the zinc that you created from the reactor and you would put it into a battery or a flow battery or even a zinc air fuel cell, whatever you wanted. So it depends on what you want to do with it. Hydrogen has extremely good energy density. And of course it depends if you're measuring that by weight or by volume. But at the end of the day, we want to create an energy economy that is simple and uses sunlight. And hydrogen is a very good candidate for that, in my mind, because when everything is said and done, you can just burn it and get all the energy out you want, and the byproducts of burning hydrogen are water.
With water being like a big issue these
Yeah.
days, I was wondering how much water is used to cool off your reactors,
That's a good question.
and is it renewable?
Yeah, I guess there's two parts to the water question, because one is, as I showed there, I was actively cooling certain areas of my reactor with water. So first of all, that water is actually a closed loop. So once the hot water comes out, we can just put it down into a cool reservoir of water, and then as the temperature drops, pump it back into cool again. So we don't actually lose any water there. But the other very important question is, if we're going to create hydrogen from sunlight and water, where's the water going to come from, especially if you're talking about a desert? So that is a very good question that needs to be addressed. And the most obvious answer in the very long-term picture is desalinating the ocean water. And it seems like a kind of a crazy thing, but that's more of a function of the availability of water right now. We really haven't been forced to do that on a large scale, but it's really simple to do. And there are desalination plants, you wouldn't even know that they exist. I mean, I grew up in the San Francisco Bay Area, and there's one in a very affluent area of the suburbs of San Francisco that's been running for 30 years. And it's completely efficient, it's cost effective, and they just decided that they didn't want to run a pipeline of water from a reservoir that was 100 miles away, so they built a little desalination plant right on the San Francisco Bay. So it's really not that complicated. So, and you can even imagine having desalination plants that are running on solar energy. So, it all fits together.
Any other questions?
Yeah, I got it.
All right, one more.
So, I'm gonna assume that you're passionate about all this. So,
Yes.
And you being from, working from, east to west, and then working out in Switzerland, do you plan on coming back to the States with your work? I mean, do you plan on impacting, because you're using the most per capita here
Yeah.
anywhere in the world.
Right.
We're basically being the leaders in destroying this earth.
Right, definitely.
So, do you plan on coming back and, gracing us with this stuff?
Yeah, it depends on the problem with the U.S., and especially in the areas in the U.S. where this kind of stuff makes the most sense, like California and southern Nevada, Arizona, is that there's a lot of regulations in place that don't favor the installation of these large facilities. Because as you can imagine, people that produce fossil fuel generate electricity don't want to see these CSP plants coming online. And there's this bottleneck of getting permits approved. Further, the price of natural gas, like I said, it's unbelievable how low it is right now. We have no idea where that's going to be 10 years from now. I would hope that it's going to be very high, because people are going to start taking into account the environmental effects, and we're going to start running out of it and everything else. But at the end of the day, if I can't find a place to install this technology in the U.S. because we can't get investors because they don't want to invest in something that's too expensive, or if we can't get permits, then maybe it's going to be installed in India or China or Northern Africa first, or whatever. But I don't think the big picture is that wherever it's installed, it's good. We need to get these things up and proven as soon as possible. That's going to be best for everyone. Yeah.
I'm not clear as to why people would object to having this. I really am not.
Yeah, but that's. Yeah, I agree.
I would not want a refinery in my backyard for sure. But what's wrong with this?
Of course, the only I'm sure once.
No. But seriously, if this was going to be somewhere near where you live, what would your objection be?
Well,
to that versus
you'd
a refinery?
You'd be surprised. You could look at the whole debate over putting the wind turbines up off the coast of Delaware, or even the single wind turbine in Lewis. People have objections for whatever reasons.
Yeah, but with all the technology that goes up, what could be better?
Well, that's true.
Renewable
And-
than that other crap.
And eventually, you can usually get around that little roadblock, but it comes down to how expensive is it going to be? What's the levelized cost of electricity? And in my opinion, I would easily pay 5, 10, 15 cents more per kilowatt hour electricity coming from a wind farm or a solar farm than I would coming from a natural gas turbine. But most people don't feel that way, and certainly people aren't willing to invest money to build these things. It's a very capital intensive business, and we need millions, hundreds of millions to build these things, and people aren't willing to give the money right now.
I say it like this, pay now, pay later.
Yeah. Yeah.
So, Dr. Croft, do you think, it's more of in this country, relating to his question, then basically we're talking about the political ramifications of they're afraid that, so-and-so with the gas industry, with the petroleum industry, they're going to lose jobs et cetera, et cetera.
Yeah, and that's, I mean, and that's a valid, I wouldn't argue with them. I mean, any industry wants to protect its jobs, and I can't disagree with them on that. You know, they're just concerned about the most important immediate thing to them. And I think that, you know, in this country in particular, we're very accustomed to being short-sighted and just planning for what we can see immediately 5 years in the future, and it's unfortunate. Yeah?
So what you've described is a process that is very low on creating environmental problems, right? I mean, you said it's a closed system.
That's right, yeah.
And then I heard a comment here that it said something about the United States creates the most amount of pollution, except that I think what we really need, I'm sorry for the politics, but we need more jobs here, and we need things to be built here. And I'm just having an aversion to exporting jobs because we can't build it here. This goes on to the regulations that you talked about. It may prohibit you from being able to build here because of, let's say, some type of prejudice. But we can build things here. I think we need to relax some of our environmental stuff so we bring it here, because I seriously do not think that China, Mexico, Indonesia, India builds things. They can build it cheaper, but we can build it a lot more environmentally safe here. And we also get OSHA guarantees that those people do not have in China or those other places.
Yeah, I mean, for the most part, I agree with you, but I think we're talking about two separate types of environmental concerns. You know, from the job side, a green energy economy can create as many jobs as anything else. So it takes a little bit of political will to decide that you want to push the economy in the green direction. The jobs are absolutely necessary. I mean, to build these plants in the desert, I'm going to need thousands of people working to build construction jobs, and then hundreds more to operate the plant later on. I mean, it's the same. It's really the business model is kind of similar to any coal plant or natural gas plant or anything else. The difficulty is the transition, because when you transition from a fossil fuel-based energy system to a solar-based energy system, the people that currently work in the fossil-based system need jobs, and they're not going to be trained to work in the solar necessarily. So that's what we're doing here at Dell Tech, right? I mean, we're trying to train the next generation of these people that are going to work in power generation, and it's going to be solar power generation. Anytime an industry shifts from one paradigm to another, there's going to be job loss, and there's going to be a lot of kickback from that. But the bigger context is that the jobs will come back in a way that hopefully, if we're using solar power, is a lot more sustainable. I mean, these solar power plants are never going to go away as long as the sun is still shining. I mean, these are jobs that will be here for theoretically billions of years. Whereas we knew from day one that our jobs related to oil and natural gas were going to run out. So it was kind of a stupid decision that we made to base our economy on that in the first place. So this transition is just very difficult, but you know, in the end, it's inevitable, and it's the best thing we can do. Yeah.
Just one thing to accent and let people see the opposition that you run into, and it doesn't have to make sense. When I was talking to my neighbors about putting up a wind turbine, my one next door neighbor was very much opposed to it. When I tried to question as to what was going on, she says, well, I think it's an eyesore, and it would make me have trouble selling my house. So, you know, I mean, you know, that's the things you run into. It doesn't have to make sense to you. It makes sense to them in their minds.
And you know, if you ask that same woman 10 years from now, if the windmill went in, what she thought of it, she probably wouldn't care. I mean, there's always an aversion to change, and it's always difficult. It's just what you're used to. I mean, one day I hope that we're all used to seeing solar panels on every roof and windmills everywhere. Yeah.
I know you said we were short-sighted a couple of years ago, but 10 years ago, you weren't here yet, and you didn't have this so
I know.
I'm going to argue that we're going to be a lot better off with you here now.
I think we'll end on that. Let's vote.
All right.